Welcome back. Today we're going to talk about solving systems of equations using linear combination, or also known as the elimination method. This is a method in which we add our two equations together, or even possibly subtract them, so that one of the variables gets eliminated, or as some people like to call it, the dropout method, because one of the variables will drop out. So, with linear combination, or the elimination method, our goal here is to get equal or opposite, so positive or negative, values on the same variable in both equations, or on the coefficient of that variable. This works best when both equations are in standard form, or at least like form when the x and y terms are aligned. And what we might have to do, we might have to multiply one or both equations by a value or values to make that happen. In other words, to get equal and opposite coefficients on one of our variables. Then, once we have equal and opposite coefficients on one of the variables, we can add the system. Okay, the variable with the equal and opposite value will be eliminated or drop out. Okay, and we do that by just adding the coefficients on the x terms, the coefficients on the y terms, and the constant. Then we will solve for the remaining variable, which will give us one answer. We know what one of the variable is. That will be half of our solution, be one part of the ordered pair, usually x or y, p or q, something like that. And then finally, we'll take whatever we got for that variable and we substitute that value into either equation. It doesn't matter, whichever one looks easiest for you, to solve for the remaining part of the ordered pair. Okay, and then your final solution is the two values that make up the ordered pair. So let's move on to some samples. We'll start with x minus 2y equals 0 and x plus 2y equals 12. As you can see here on the y variable, we have equal coefficients. They're both 2, and they have opposite values. One is positive, one is negative. So we should be able to simply add up our system. So I can add that system together. X plus x, I get 2x equals 12. I divide both sides by 2. And x equals 6. So now I know what x equals. I can substitute that into either equation. So 6, our x, plus 2y equals 12. Subtract 6 from both sides. I get 2y equals 6. Divide by 2, and I get y equals 3. So my solution to the system is the ordered pair 6, 3. So if I graphed these two equations, this is the ordered pair that they would meet at. Those two lines would intersect and meet at the ordered pair 6, 3. And of course, 6, 3 satisfies both equations. We'll do the second one. I'm going to change this one a little bit. We're going to make that a negative 2. So we have 9x minus 10y equals negative 2, and 9x plus 2y equals 22. Well, here we have equal coefficients, but they're not opposites. So I'm going to multiply this entire bottom equation by negative 1, or I'm going to subtract it. So I'll rewrite the top one. 9x minus 10y equals negative 2. And the bottom one becomes a negative 9x minus 2y equals negative 22. Now I have equal and opposite coefficients. The x's are going to drop out when I add the system. So negative 10 and negative 2 is negative 12y equals negative 24. Divide by negative 12, and we get y is negative 24 over negative 12, which is a positive 2. So now I know that y is 2. I just need to solve for x. So 9x minus 10y equals negative 2. Doesn't matter, I can substitute into either equation. I chose the top one. 9x minus 20 equals negative 2. Add 20 to both sides. 9x equals 18, and divide by 9, and we see that x equals 2, so our ordered pair is 2, 2. That's the solution to our system. Sample problem number 3, looking a little bit more difficult. We have fractions here, so you'll see sometimes we want to maybe multiply everything by our common denominator. We might want to multiply all this by 6, and we could do that top and bottom. But if I look here, I have equal and opposite coefficients on the y. So if I have equal and opposite coefficients and I have a common denominator in the 1/2 and the 5/2, I am ready to just add this one up. 1/2 and 5/2 is 6/2 x, or what you'll know as 3x, equals 8 plus 4 is 12. So we get 3x equals 12, and dividing by 3, we get x equals 4. So I know my x value is 4. Substituting into either one of these equations, again, I'm going to choose the top one. 1/2 times 4 plus 1/3 y equals 4. 1/2 times 4 is 2. 2 plus 1/3 y equals 4. Subtract 2 from both sides. So I have 1/3 y equals 2. Well, I need y, so I'm going to multiply both sides by the reciprocal of 1/3. I'm going to multiply by 3, our property of reciprocals. So that would give us y equals 6. So the ordered pair for our solution is 4, 6. And I'll leave the check to you. Number 4, a little more challenging. We don't have equal coefficients. We don't have opposites anywhere. We want to eliminate one of the variables. We could multiply the top one by negative 2. That would work for us. We could multiply the bottom one also by negative 2. That would work. But that would eliminate the x's, and I think that's what I'm going to do. I'm going to multiply the bottom equation by negative 2. So that would become a negative 6x minus 4y equals negative 18. So now I can simply add the top equation and this bottom equation. So 6x and negative 6x, there's my x drops out. Y minus 4y, well, that would be a negative 3y. And 6 plus a negative 18 is negative 12. Divide by negative 3, and I get y is equal to positive 4. So I know what y is. I want to solve for x. So 6x plus 4 equals 6. Subtract 4 from both sides, I get 6x equals 2. And dividing by 6, I get x is 2/6 or 1/3. So my answer is the ordered pair 1/3, 4. That is the x and y that will satisfy that particular system. And we can still get things like no solution. Here we might get some different answers. We could get an equation that the lines are parallel, or we could get the same line. Okay. Just as a side, if we happen to get like x equals x for some reason. I don't know why that would happen. We might get something like, better yet, we might get like 4 equals 4. Okay, well that's a true statement, so that would be like in all real numbers. That means there's going to be an infinite number of ordered pairs. Okay, that would work. Any ordered, and there's an infinite number of ordered pairs that would work. So those two would be the same line. If we would get something like 2 equals -7, well then we know we have parallel lines, and then there's no solution. So just a little aside here. So if we come up with different answers, we can get parallel lines, or if we get something like something equals itself, okay, there's an infinite number of ordered pairs, and that would be the same line. Let's move on to something that's a little less challenging, I guess. But we've got decimals here, and what we want to do is we want to eliminate our decimals. Okay, so really I would multiply both of these by 10, both the top and the bottom by 10. So I get 3x plus 5y equals 310, and I get 2x minus 1y equals -10. So I have opposites on the y's, but not equal, so I'm going to go ahead and multiply the lower equation, the second one, by positive 5. I'll go ahead and rewrite that top equation. 3x plus 5y equals 310, and the second one, I will rewrite that one. So 5 times 2 is 10x minus 5y equals -50. And I will go ahead and add these up. 13x equals 260. Divide by 13. And x equals 20. And I can substitute into any equation. I am going to pick substituting into that one. I think the numbers are going to be easiest substituting into 2x minus y equals -10. So 2x, 2 times 20, minus y equals -10. So I get 40 minus y equals -10. I subtract 40 from both sides. The opposite of y equals -50, and I get y equals 50. That was pretty straightforward. So my ordered pair, 20, 50, is the solution to my system. Problem number 6, a little bit similar to 5, where we're going to have to multiply. We have opposite coefficients, so what I would do is I would multiply the top one by 2 and the bottom one by 5 and come up with 2 new equations. And you know what? For a little practice, why don't you stop the video here, take a break? Why don't you go ahead and solve that particular equation? And I'll check your answer in class. So welcome back from doing that particular problem. Hopefully you got the correct answer. We'll find out in class tomorrow. Let's take a look at this one. Now we've got x and y in the denominator. This one looks a little complicated. We might want to multiply top and bottom by xy, but our common denominator. But we also have a common denominator x and a common denominator y, and we have opposite coefficients here on y. I'm going to go ahead and multiply the top equation by 5. which would give us the fraction 5 over x plus 5 over y equals 25. Now I have equal and opposite numbers here with the y's, and I have a common denominator, so I can simply add that up. So I end up with a 3 over x plus a 5 over x, which adds up to 8 over x. The minus 5 over y and the plus 5 over y cancel, and negative 9 and plus 25 equals 16, which is 16 over 1. And what I have here is a proportion. So as you know, in a proportion, we've seen this before, I can cross multiply. So I get 16x equals 8. And I can solve for x. 16 times x, I divide both sides by 16. I recommend you show your work here. And 8 over 16 is 1/2. And that's a positive 1/2. So we get 1/2. So all we need to do now is solve for y. So 1 over 1/2. I'm going to go substitute into the top equation 1 over x. So 1 over 1/2 plus 1 over y equals 5. Well, 1 over 1/2 is really 2. 2 plus 1 over y equals 5. I subtract 2 from both sides. I get 1 over y equals 3 over 1, or 3. And just like we cross multiplied here, we can do the exact same thing. Because we have a proportion, 1 times 1 is 1, so we get 3y equals 1. We divide both sides by 3, and y equals 1/3. So the solution to our system here is 1/2 for x, 1/3 for y. And if you look back, you will see that that does satisfy both equations. So when you go ahead and check your work, you'll see that works. So that wraps up our elimination or dropout method. That's a very effective method, and we will use that for many things in the future as well. So we will see you in class.